Greetings, everybody. Let's begin our discussion of eigenvalues and eigenvectors. Now, what we've seen so far in examples of linear transformations are that we've seen rotations, we've seen reflections, and we've seen scalings. With rotations, we imagine that we've got this some vector that's pointing in this direction as being our axis of rotation, and our entire space is then being rotated around that particular direction. We've seen reflections where we've got this plane that's passing through the origin and we're reflecting across that particular plane. And then scalings that really we're just taking a vector, we're not really changing the direction, but we're just either making it longer or shorter in particular directions. Now for rotations, as we said just a second ago, that rotations, we've got a fixed axis. So the axis in that particular linear transformation is not being moved. That axis is staying exactly where it is. Likewise, for the reflections, if we take vectors that were already in the plane through which we're reflecting, those vectors are not moving. They're still staying in exactly the same position from which we started. And so what that leads us to is this notion of looking at, if we have just a general linear transformation T, that we might very well ask, well, what vectors does this particular transformation leave in the same direction? What directions are really not changing? Now, in asking that question, it leads us to the equation where if we take a vector, we apply our linear transformation T, that's just being scaled by some scalar lambda. So it's maybe lengthening it, shortening it, maybe it's reversing its direction, but we're not really changing to a different direction. We're just kind of maintaining the direction from which we have, or the opposite of that direction. And so that leads us kind of to this natural equation, T of x is equal to lambda of x. Now, if we kind of take that just a little bit further, we can start with T of x is equal to lambda of x. We move the lambda of x to both sides, and we factor out our x, so we get T minus lambda times x. Well, T, remember, is going to be an n by n matrix. Lambda is just a scalar, but if we kind of play this thing of, we can take this lambda times the identity matrix, which then also makes it an n by n matrix. So we've got an n by n matrix minus an n by n matrix, so that result is an n by n matrix. So this gives us a new linear transformation, T minus lambda I times this applied to this variable x, this vector x, gives us 0. And so we can say, well, when is that going to have a non-trivial solution? Exactly when the determinant of that linear transformation is going to be 0. Now, determinants are just scalars, and so if we kind of make this a function of lambda, P of lambda is equal to the determinant of this linear transformation, then what we actually get is that this is going to end up being a polynomial in lambda, and in particular it's going to be a polynomial of degree n in lambda. So kind of our finding the roots, so finding the values lambda, the roots of this polynomial, is going to then lead us to values where we can have a non-trivial solution, and that will give us the fixed direction vectors that we're actually looking for. So these values, these roots of this P of lambda, are really what are called the eigenvalues for the matrix T. Okay? And this polynomial in and of itself, the determinant of T minus lambda I, is what we refer to as the characteristic polynomial for T. So now if we're given an eigenvalue lambda, then that kind of leads us back through the logic that we've discussed, gives us a non-trivial solution. So choosing the right value of lambda allows us to have a non-trivial solution to t minus lambda I of x is equal to 0. So that tells us that the subspace, our kernel, so the kernel of that linear transformation t minus lambda I, the kernel of that thing is what we then refer to as the eigenspace of t corresponding to our eigenvalue lambda. And so kind of what we've gone through up to this point is giving you some of the definitions, kind of giving you some of the verbiage of eigenvalues and eigenvectors, characteristic polynomials that we'll kind of talk about and go a little more in depth to in the next video, and I will see you guys then.